Hello, statisticians. Mr. Youngsaver here from Skew the Script. Today we're going to introduce ourselves to probability by looking at a couple of examples. The first one is looking at baseball statistics and specifically the most improbable streaks we've seen in the major leagues in our lifetime. The second one, a lot more serious, is looking at police use of force statistics and race through stop and frisk data set. Let's skew it. Today's lesson is defining probability. This is lesson 5.1 in our course sequence. Let me introduce you to Chris Davis. He's a Major League Baseball player and he plays for the Oakland Athletics. Let me also introduce you to Chris Davis. He's a Major League Baseball player and he plays for the Baltimore Orioles. And both these players set these amazing records in the past few years. And I want to explore today for our first key analysis, how improbable were the MLB records set by the two Chris Davises in the MLB. Another much more serious topic we're going to be talking about today through data and probability is the probability of being stopped by police equal for all racial groups? If you'd like to follow along using guided notes, please go to this URL here. So first, we're going to talk about defining probability in terms of the law of large numbers. The law of large numbers states that after many trials, the relative frequency of outcomes will approach their probability. If you don't quite get what that means, that's all right. I have a simulation here for you. This is a publicly posted simulation. It's very good. Please go to the link. You can type it in there or go to the description to find it. And please follow along as I go through the applet. So this simulation takes us through tossing a coin. This is a fair coin, 50% chance of heads, 50% chance of tails. And when we toss it, we're going to count the number of times we've had a heads and see, will actually 50% exactly of those tosses be a heads? So let me do one toss. That one happened to be a tails. So there are no heads yet. We don't see any on data set here. But the next one happened to be a heads. So now exactly 50% of our tosses are heads. We can see that our relative frequency of heads has approached that magic 50% number that is the theoretical probability for this process. And 2 is not really a high enough sample size to keep on doing it. We happen to get into our tails, okay. Happen to get heads again, okay. And let's keep on going. And eventually, you can see there's gonna be some variation. But the law of large numbers states that the relative frequency, the proportion of these tosses that should be heads, will approach 50% in the long run. So to speed that up, I'm going to go toss, 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 toss. We see we're varying a little bit lower than expected number of heads, but we should approach it. We should approach this green line, the magic green line, 50% heads. So I'm going to speed this up. I'm going to do 25 tosses per click here. Toss, 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 toss. And we're getting there, getting there, getting there. I'm going to speed it up even more, 200 tosses per click. And you can see here, as that's going, we are approaching, and getting there, getting there, getting there. We will eventually approach that 50% mark and be very, very close to exactly 50%, as you can see here. So this is what the law of large numbers states. The more times you repeat a chance process, the more trials you will begin to approach the relative frequency predicted by theoretical probability. Now, this applet brings up one myth that I want to tackle together. This is the myth of being due for one. Say that you have a fair coin and you flip it 10 times. In which situation is getting a tails on the next flip more likely? Here's situation 1, heads, tails, tails, heads, heads, etc. And situation 2, heads, tails, tails, and then a bunch of heads in a row. So in which situation is the 11th flip going to be more likely tails? Well, a lot of people will say situation 2, you've got a bunch of heads in a row, you're due for a tails on your next one. That is completely false. The tails is equally likely in both situations. The prior events have no bearing on the probability for the next flip because the events are independent. Probability doesn't change because of previous results if you have independent coin flips. This is the myth of being due for one. And let's talk about that myth in terms of a more practical example in baseball. And I call this the tale of two Chris Davises. Let's first talk about Chris Davis with a K, and then we'll talk about Chris Davis with a C. Chris Davis with a K in 2015 had a batting average of 247, and he had 27 home runs. For those who are unfamiliar, a 247 batting average means that 24.7% of his at-bats ended in a hit rather than in an out. Chris Davis in 2015 had a batting average of 262 with 47 home runs. He actually led the major leagues that year with those 47 home runs. He was a huge power hitter. He also led the major leagues in terms of neck size. Look at that thing, like a tree trunk. Very impressive. Now, in 2018, he had only a batting average of 168 and only 16 home runs. He was kind of in the downhill trajectory in his career then. And that batting average was really, really low. We're going to investigate why. Here's May 2018, about a month into the season. He got 0 hits in his first game in May, 2 hits in the next game in May, 1 hit in the following game, 1 hit in the following game, then 0, etc. So it's a mix of games where he had no hits, multiple hits, or just 1 hit. Zoom forward to September of that year. He has, on September 14th, 1 hit. And then he had 0 hits the next game, 0 hits the game after that. And then for the following games, until the end of the season, he has no hits. So after September 14th, he's completely hitless. Bit of a slump, bit of a downturn. But we start the next season very hopeful because he must be due for a hit. He had a bad slump at the end of the year. Maybe he retooled some things over the offseason. He's ready for getting a hit now. Start in April, opening day, 0 hits. And then the following game, 0 hits, 0 hits, 0 hits. Okay, he's got to be due for a hit now. He's just got to be. 0 hits, 0 hits, 0 hits. Until 17 straight hitless games transpire between the end of the previous season and the 2019 season. Finally, he gets 3 hits in one game, April 13th. He comes in with a bang, and he ends the drought. That was 54 straight at-bats in those games without a hit. That is a major league record, and to put that into context, MLB's modern era began in 1900. So all-time records are rare, and Chris Davis set one between 2018 and 2019. It was such a big deal that he asked for the ball when he got his hit that broke the streak. He's in the record books. His teammates were celebrating. It was very funny. And this, again, gets at the due-for-one myth. So unlike coin flips, Chris Davis's chance at getting a hit isn't the same for every at-bat. However, I would argue that the due-for-one logic here is still flawed. Repeated failure doesn't indicate a higher chance of success on a future attempt. If anything, it indicates that your original estimate of the probability of success was already too high. Now let's talk about the other Chris Davis. In 2015, as I said, his batting average was 247. In 2016, his batting average was also 247. 2017, it was also 247. And then in 2018, it was also 247. He had different amounts of at-bats each year, and he got that sweet spot number of hits to get the 247 batting average each of those 4 consecutive years. That is the, by far, longest batting average, same batting average streak in MLB history for the number of at-bats that Chris Davis was taking. And in 2019, unfortunately, the streak was broken. He probably was due for a season where he didn't have a 247 average. JK, we don't believe in the due-for-one myth here, but I wanted to mention his streak as well because it was also so improbable. Now, let's talk about how we define probability, and we're going to talk about the simple definition first. We can define probability as the number of outcomes in a certain event divided by the total number of possible outcomes. We call this a simple definition because we only use it when all outcomes are equally likely. So let's look at one example where that's the case. Say there are 8 red marbles and 12 blue marbles in a jar. What is the probability of selecting a red marble from that jar? So let's define the event. R is the event of selecting a red marble from the jar, and P of R is the probability of event R occurring. In other words, the probability reach in and grab out one of the red marbles. So we can model this as P of R is equal to the number of outcomes in event R, the number of ways to get a red marble, divided by the total number of possible outcomes. The way we model that is we take the number of red marbles and divide it by the total number of marbles, which is the 8 red plus the 12 blue. And that is 8 out of 20, or 0.4, which is also 40%. That's the probability of selecting a red marble. So let's talk about the properties of these simple probabilities. So a few properties. 1, probabilities are always between 0 and 1 inclusive. You can't have a negative probability, you can't have a probability over 100%. And in this case, probability of red was already 0.4, we're good. The probabilities of all possible events must add to 1. If you account for all possible events, their probabilities have to add to 1 because something has to happen. So in this case, there are 2 possible events. You get a red marble, you get a blue one. So those probabilities should add to 1. Probability of blue is 12 out of 20. So that's 0.6. 0.4 plus 0.6, we get 1. We're good. Now, the last one I want to talk about today is the complement rule. That means that the probability of event A not happening is equal to 1 minus the probability A does happen. We call the complement PAC. That C means complement means not A. So probably A does not happen. Let's look at an example here. So according to this rule, PRC, so the complement of R is 1 minus the probability of R, meaning the probability that we don't get a red marble is equal to 1 minus the probability we do get a red marble. If we don't get a red marble, we must have gotten a blue one. So the complement of R is simply blue. So the probability of getting a blue marble should be 1 minus the probability of getting a red marble. So we do the math, and it is. Those probabilities do match. Let's talk about now probability models. So a probability model lists a set of outcomes and their probabilities. Here are the two properties of a probability model. All probabilities are between 0 and 1, and all probabilities in a probability model must add to 1. We have to check these when we have probability models. So let's look at another very simple example just to get our feet wet in probability. Say you have a bag of 20 beads. They're a mix of clear solid beads and red/green beads. So you could have a clear bead that's transparent, but it could have a red or green hue, or you could have a solid bead where you can't see through it, again, red or green hue. Say there are 6 clear red beads, 8 red solid beads, 2 clear green beads, and 4 green solid beads. If we drew out one bead completely at random, this would be the probability model. There was 6 clear red beads out of the 20 total, so that's a 30% chance, and the rest are defined there. Now, let's check that this is a valid probability model by checking these two properties. All probabilities must be between 0 and 1. That is the case. We see they are. All probabilities must add to 1. Let's add them up. They should add to 1. All outcomes have been covered. 100% of the probability is there. Good. Now, let's define a couple events. Say that event R is the event of selecting a red bead. Now Q, which is just a random letter I picked out, is the event of selecting a red solid bead, specifically a red solid one. So let's find the probability of Q. Well, thankfully the probability model makes this very easy for us. Probability of Q is simply the red solid probability right there. Probability of R, so that could be a red solid or a clear red. Any red one would do. So we add up those two probabilities and we get 70%. So 70% chance the bead we get out is a red one. Find the probability of Q complement. That means the probability of not selecting a red solid bead. So any bead except for the red solid one. So we cover up the red solid one, so it could be any of those other 3 options, and we can add those together. Another way we could do that is by using the complement rule. So we knew that the probability of getting a red solid bead was 0.4. So if we do 1 minus that, we also get the same probability, 60% or 0.6. Last but not least, let's find the complement of getting a red. So that means we have to draw out a green bead. So we add up the green probabilities, or you could do 1 minus the probability of getting a red bead. Because it was 0.7, it's 1 minus 0.7, or 30%. So we're gonna close out today with the discussion. And let's talk about the stop and frisk program. During stop and frisk, New York City police officers were allowed to stop people in public if they had a reasonable suspicion the person might soon commit a crime. This was part of a policing reform that positioned police to be proactive rather than reactive. Instead of responding to calls, they can make the call themselves and potentially stop future crimes. There's a problem with this, though, and this is a quote from a couple criminology professors. The low burden of proof, the large discretion granted to police, and the relatively invisible nature of these sorts of encounters when you stop people on the street combine to create real potential for abuse. And if you look at the stop and frisk data as reported by the police, of the millions of stops during the program, only about 12% of all of them resulted actually in an arrest or summons. So 88% were not stops that were actually something that is actually arrestable or even a summons. So one question people have asked is, are police biased in who they choose to stop? So we looked at this data before, we're gonna look at it again. This is a random sample, and it's also a representative sample of the 2011 data from the program as reported by police. We had the 3 predominant racial groups in the data set among suspects, Black, Hispanic, and white, and we had the force levels used against them according to this breakdown. Now, if we calculate the marginal distribution just of race in terms of who was stopped, we find that there were 55 of these 3 racial groups, so among just the 3 racial groups, 55% were Black, 35% were Hispanic, and a little less than 10% were white. And so we can take those proportions and compare them to the actual population of New York City. Here's the New York City population breakdown according to the American Community Survey in 2011. So the discussion question I'm gonna leave you with today is, if stops were done completely at random, so there's no bias, no chance of any kind of human decision-making here, it's completely random stops, which groups will be stopped proportionally more often? Which groups will be stopped proportionally less often? And what conclusions can you draw from this comparison? That's it for today's Statisticians. Thank you so much. Have a good one.